Hello, welcome. In this video we are going to discuss a concept in number theory that is called the exponent of a given number mod m. The concept is the exponent of a given number modulo m. And we will, after defining that concept, we will discuss some of its properties. See, two numbers must be given to define the exponent. Let a and m be the two numbers, two numbers given, two natural numbers given which are relatively prime. A and m be two relatively prime integers with the property that m is greater than or equal to 1. Then we consider we consider all positive powers of a. That's a to the power of 1, a to the power 2, a to the power 3, etc., etc. we consider. So if we go considering these powers, we can see that after some stage we get that a number, we get a number, or we can give a number, we can find a number in this sequence of powers, such that when we divide that number by the second number m, we get 1 as the remainder. What actually tells us about this this thing very firmly, or what does it make us to give this statement very firmly, that it is the Fermat's theorem. You know that Euler-Fermat's theorem that states that a raised to phi m, a to the power of phi m is congruent to 1 mod m. We know that we have learned that Fermat's that Euler-Fermat theorem here which in the when it is stated, then we can say that it is a raised to phi m is congruent to 1 mod m, where phi m is the number of numbers, it is the number of numbers which is less than m and relatively prime to m. Okay, so one thing is clear, that there exists at least one number. There exists at least one number. That number can be taken equal to phi m, which satisfies the condition that a raised to f is congruent to 1 mod m. When we replace f by that number, you get you can see that this congruence equation is satisfied. So after knowing that there exists at least one number, you can ask a question whether there exists some number which is less than that number. So naturally there you can conclude that you can conclude that question by giving the answer that of course there exists some number which is less than, or if there does not exist, that will be that number which have the minimum value, which has the minimum value. So of course there exists, we can thus conclude that there exists some number which has the minimum value and also that satisfies the relation a raised to f is congruent to 1 mod m. So it's because since there exists at least one number at the place of that can be used at the place of f, that number is phi m, clearly that number is phi m, and then there must exist some number which has the least value, the lowest value having this property. So that motivates us to define the exponent of the given number m with respect, or modulo m, or with respect to the given the second number m. See the definition: exponent of a number m, number a mod m. Exponent of a number a mod m is the smallest positive integer. See, it is the smallest positive integer f such that a raised to f is congruent to 1 mod m. See, this congruence equation is taken in the form which is stated here, which is mentioned here: a raised to phi m is congruent to 1 mod m, or a raised to see, this one itself, a raised to f is congruent to 1 mod m. So there exists then there exists a least number that can be substituted for f in this equation, a raised to f is congruent to 1 mod m, and you can see that that equation is then satisfied by that number. So that number will be called the exponent of the given number a with respect to or modulo m. So we write that number, and now at this moment onwards we will call that number f, and we can also represent it. Another way of representing that number is exp of a with respect to m, or exp of a modulo m, mod m. It is read as a exponent of a mod m. It is that number f. So this is the number having this property, having the least value, and also having that property, having the property and having the least value, or the smallest number. And also you can see that in some cases exponent of a to the base m or exponent of a modulo m will be equal to, in some cases only, will be equal to phi m itself. So in such a situation we say that a is the primitive root mod m. So when can we say that a is the primitive root mod m, or what is the condition that a is the primitive root mod m? If exponent of a mod m is equal to phi m. If exponent of a mod m equal to phi m, then we say that a is the primitive root mod m. In other words, we can say that a is the primitive root mod m, and if a is the primitive root mod m, then there does not exist any number which is less than phi m. There does not exist any number which is less than phi m or having value less than phi m, such that a raised to f is congruent to 1 mod m, where that number you can consider f as as the number which is less than that value, having that value which is less than phi m, okay, or having the value less than phi m. Now we can discuss some of the properties of the exponent of a given number a with respect to or modulo m. There are three results given here in theorem 10.1, and that result can be proved. We are going to prove that result. So the statement, let's read that. Let's go through the statement of the result. Given m greater than or equal to 1, and also the GCD of a and m equal to 1, let f equal to exponent of a to modulo m. Let us take that f is equal to exponent of a modulo m. Then we have the three statements. Then we have to prove that the three statements are true. First statement is a raised to k is congruent to a raised to h mod m if and only if k is congruent to h mod f. Once again, a raised to k is congruent to a raised to h, where k and h are two positive integers, right? Okay, and then a raised to k is congruent to a raised to h mod m if and only if the two positive integers k and h are congruent with each other mod m. Mod f. The change you may note that here we take mod m, and here, but in the case of that exponents, we take that that power values, we take that as modulo f, mod f. So that means we divide this quantity, the difference of this quantity, by f, not by m. So a related property there exists, but after proving this the statement a, you can prove the statement b very easily, and that says that a raised to k is congruent to 1 mod m. A raised to k is congruent to 1 mod m if and only if k is congruent to 0 mod f. In particular, f can divide phi m. Also says that in all the cases you can prove that f can divide if f is the exponent of a mod m, then f can divide the number phi m. Okay, then the third statement says that when we consider the consecutive powers of the number a, 1 a square, etc., a raised to f minus 1, and these numbers are all incongruent mod m. They are all incongruent mod m. That means, what does that mean? That statement. It means that when we consider these numbers 1 a square, etc., up to a to the power of f minus 1, and you divide these numbers by the number m, When we divide these numbers by the number m, and you examine, you compare the remainders that you are going to obtain, none of these remainders are the same. Actually, that means when we divide these numbers by the number m, you get remainders. That's sure. You are going to get some remainders, and these remainders, when you compare these remainders, you can see that these remainders can never be equal. So that's the meaning of the last statement. So let's consider one by one the statements, and we are going to prove these statements. Okay, first let's prove the statement A. So to begin, the proof of the statement A, we accept that, or we think that a raised to k is congruent to h mod m is true. We accept that it is. We accept which statement true? We accept that a raised to k is congruent to a raised to h mod m. And also, k cannot be equal to h. Normally, you cannot take k equal to h, because, and that's a special case, and that situation is avoided. There is nothing to prove in that case. If k is equal to h, then if k equal to h, then you can say that k is then congruent to h mod m, because the same quantities are there. K and h are the same quantities, so their difference can divide by mod f. So in that situation, it is easily proved. It's easily completed. The proof of that part, that means if k equal to h, that part can easily be completed. You can show that this happens. So we think that one of the number k, either k or h, is greater than the other. So for convenience, you can assume that, you can think that k is greater than h. Otherwise, suppose h is greater than k, you can then revise the order, which is order of this number, and then you can rename them after revising the order, and then rename them after, and you can rename the numbers, so that you can write that k is greater than h. Okay, so there is no problem by assuming that k is greater than h in this situation, and then you can then proceed. So what does then it means when k is greater than h? You can then, what does the statement, the given statement mean, which is accepted as true? And that means when you subtract h raised to k from a raised to h from a raised to k, and that number can be divided, you are going to get a number that can be divided by m completely, or that can be written as r into m, where r is some integer. So a raised to k minus a raised to h equal to r into m, where m is here, this the number taken here. So r into m, where r is some suitable integer, and that value of r depends on the quantity that we take here. Okay, then what we can do next, here you can see that then this implies that when we take, since h is less than k, since this is the statement which is true, so you can take a raised to h outside. So h is a number which is less than k. Both are integers and positive integers. So by taking h outside, you can write that this expression equal to a raised to h into a raised to k minus h minus 1. See, this quantity a raised to h will go outside the bracket. Then okay, then you get a raised to k minus h is the remaining quantity the first time, and the second time will be then 1, equal to the same situation, r into m will be the product of r and m. And we know that, since we know that the GCD of a and m equal to 1, there is no number which can divide both of these numbers, and that means then m, you can then say that m cannot divide a. So you can say that m cannot divide a. If GCD of a and m equal to 1, then m cannot divide a. That's a fact. So as a consequence, m cannot divide any power of a. Since m cannot divide a, m cannot divide, this is m cannot divide a raised to h, a to the power of h, where h is some positive number, greater than it's some positive number. And that implies that m can divide. See, so then m must divide. Since m can divide this product and m cannot divide a raised to h, then m must divide a raised to k minus h minus 1, right? So m must divide a raised to k minus h, a raised to k minus h minus 1. That quantity must be divisible by m. and that's written here. So m can divide a raised to k minus h minus 1 taken together, and that implies that see, when m can divide a raised to k minus h minus 1, that implies that a raised to k minus h is congruent to 1 mod m, right? So by rewriting this in the congruence form, in the congruence relation, as a congruence relation, you get that a raised to k minus h is congruent to 1 mod m. And at this point you can think about you can think about this is the time to think about that exponent of the number a. What does that mean? Exponent of since f is accepted as the exponent of the number a mod m, it means that f is the least positive integer that can have the property that a raised to f is congruent to 1 mod m. See, f is the least number having the property that a raised to f is congruent to 1 mod m. But one more fact we have now we have established by our based on our previous mathematical derivations or the mathematical steps that we have developed in our previous steps. Previously we have developed, using that we know that a raised to k minus h is congruent to 1 mod m. That means k minus h is also another number having that property when it is used as the power of a. And when you after that, if you divide that number, that the power of a, when you divide that number by m, then you get 1 as the remainder, right? Okay, that is a raised to k minus h is congruent to 1 mod m. But since f is the least integer, least positive number having this property, you can say that, and you can very clearly say that k minus h must be greater than or equal to f, right? So k minus h must be greater than or equal to f. So we have those two situations. First situation is k minus h equal to, we have two different situations, two cases. In the first case you can say that k minus h equal to f, right? Then k minus h equal to f, that means k minus h is divisible by f. In that case you can write that k is congruent to h mod f, and we can then end with that with this statement. So in this situation, in which situation actually, that is in the first case, that is when k minus h is equal to k minus h is divisible by when k minus h equal to 1, and that is the situation, the first case, that is k minus h equal to f. When k minus h equal to f, then f can divide k minus h, therefore k is congruent to h mod f. Thus we have that the expression or the congruence that we are looking to prove. Okay, therefore you need to consider, since we have in the first situation we have completed the procedure of the proof, we need to think about the remaining situation, that is k minus h is greater than f, right? That is the remaining situation where k minus h is greater than this quantity k minus h is greater than f. Okay, when k minus h is greater than f, you can when this quantity k minus h greater than f, you think about dividing that quantity, because f is less than k minus h. F is a quantity which is less than k minus h, so you can think about dividing k minus h by f. And when you divide that greater quantity by the smaller quantity f, then you get a remainder as quotient, and also you will get quotient and remainder. Okay, then q will be the quotient. Suppose q is the quotient and quotient, and r is the remainder. Then definitely you can write that 0 will be the remainder. 0 will be less than or equal to 0 is less than remainder r. You can say about you can give a condition about that remainder, that is 0 will be less than or equal to r less than f, right? Okay, that you have that kind of you have earlier you have many situations you have seen this kind of situations in this kind of expressions, when a quantity greater than some other quantity, and you can divide that smaller quantity the greater quantity by the smaller quantity, and you can write it as in terms of the remainder and the quotient. and also the quantity which is less than the first quantity, which is less than the other quantity. Okay, so that is the situation that we write here. Since f is less than k minus h, and you divide k minus h by f, you get a quotient q and a remainder r. Then the remainder r satisfies the condition 0 less than or equal to r less than f. And so you get the you get that in this situation you can write that k minus h equal to q into f plus r. Okay, and then what we are going to do next, you are going to substitute it. You are going to substitute or use this quantity. You can use this quantity in this expression. Nothing, you are going to you are going to continue this expression. Okay, then you can see you come back to this expression a raised to k minus h is congruent to 1 mod m, and there you then it is then revised, its order is then revised, and you can write 1 is congruent to a raised to k minus h. Okay, after that you can replace this k minus h by qf plus r together with this condition. It is there, you can keep that condition aside, and you can then substitute. After substitution you get that a raised to qf plus r is then okay, you get this, and we are now going to establish that this is congruent to a raised to r mod m. How? No, that you can do. It's because, and you can explain that, or you can understand this this step, this development here. You can understand this development or the changes here by considering these two steps, steps 1 and step 2, or the expression 1 and 2 numbered here. And that's because you know this you know that this expression can be written as a raised to kf into a raised to r, right? This can be splitted, and this product can be splitted into two factors, and first factor is a raised to q into f, and into then the second factor is a raised to r. And then thinking about a raised to qf, the first factor a raised to qf, you can write that equal to a raised to f the whole raised to q. Okay, a raised to f the whole raised to q. But you know that according to our assumption or the definition or the meaning of you applying the meaning of f, you know that a raised to f is congruent to 1 mod m. Okay, that you know a raised to f is congruent to, since f is equal to the exponent of a. So we know that you know that when it is the exponent, then you can write a raised to f is congruent to 1 mod m, and f is the least number having this property. And what you can do after that, you can now take q copies of the same expression. We consider q copies of the same expression. That's a raised to f is congruent to 1 mod m, a raised to f is congruent to 1 mod m, etc. How many times? Q times. After taking this q copies, q times this q copies, all these equations, all these are congruence equations, and they are multiplied together. And that multiplied together means you can multiply the left hand side expression, and that can be congruent to the product of the right hand side, modulo. Then you can write modulo m. So when we multiply these q expressions, that you know that it's equal to a raised to f into a raised to f into etc. q times that product contains q times q factors and equal to then congruent. It is then you can use the same congruent symbol. It will be congruent to 1 into 1 into 1 into q times. So that will be that product will be 1. Then you can write modulo m. Finally you are going to get nothing but this expression, this q a raised to qf. A raised to qf is equal to a raised to f the whole raised to q is congruent to 1 mod m. This is the expression that you are going to get. So actually I have explained the steps behind getting this or writing this expression. Okay. Thus a raised to qf is then congruent to 1 mod m, and again you know that a raised to r is congruent to a raised to r mod m. That's very natural and very simple actually, because every natural number can be written congruent to the same number modulo any number, any non-zero number actually, that you know. It's a very simple Yeah, it's a fact. It's a very simple fact. So therefore, considering these two expressions, and after that, after writing this, you can then multiply once again, apply that multiplication rule once again, considering this as the in the expression 1, this is the first number, and then second number, this is the first number, second number in the second expression, and you can multiply left expressions, left hand side you can multiply, and that will be equal to, that product will be equal to the product of the right hand side, and that is a raised to qf plus a raised to qf into a raised to r, a raised to qf into a raised to r, that is a raised to, when we combine we get the a raised to qf plus r, is then congruent to 1 into a raised to r, that is a raised to r. Okay, therefore we get this expression, this congruence also we get, a raised to qf plus r is congruent to a raised to r mod m. And now a raised to r is therefore we get that since we have started here, and 1 is then congruent to a raised to k minus h is that quantity equal to a raised to qr a raised to qf plus r, and that again is congruent to a raised to r mod m. Therefore you can directly combine these two numbers. Thus 1 is then congruent to, it's as its direct consequence. So thus we have verified this the validity of this expression, the truthness of this expression is verified. After that, you can take the first number and the last number, you can join them together by using congruence. Thus we get that a raised to r is congruent to 1 mod m. See, we have seen that the relation for r and f, when we compare r and f, we have seen that r is less than f. So this is that relation that exists about r and f. When we compare the values of r and f, we know that r must be less than f. But also we get that here finally at this moment you can say that a raised to r is congruent to 1, a raised to r is congruent to 1 mod m. And also you think in just a moment, you can think about the meaning of f. F is the least number. F, that f is the least number, the least integer, least positive integer, having the property that a raised to f is congruent to a raised to f is congruent to a raised to f is congruent to 1 mod m. So this property is possessed by only so that means no number less than f. And since f is the least number having this property, it means it's very clear that no other number less than m can possess this property. But some other way we have proved that there exists a number r which is less than f. There exists the number r less than f such that a raised to r is congruent to 1 mod m. See, these expressions are actually contradicting. These are actually contradicting only except one case. So since they are contradicting, if they are contradicting, then we cannot leave this situation and go back actually, because there is one possibility actually, there exists one possibility for this statement to be, for both statements to become true. The same time, simultaneously, the statements, both statements, that is a raised to r is congruent to 1 mod m and a raised to f is congruent to 1 mod m, can go together, can go hand in hand only if you assume that r is equal to 0. See, r can be equal to 0 also. So when r equal to 0, there is no problem, that quantity will be, that part will be then nullified when r equal to 0. If you assume that r equal to 0, when you come back to this expression, then this part will be equal to 0. When this is equal to 0, then you get that a raised to qf alone is then congruent to 1 mod m. Okay, that expression is there, and that is true also. Okay, so only one, in order to escape from this contradiction, you get in all the other situation when the value of r is greater than 0 and less than f, all those situations will lead to a contradiction. So you cannot, since you cannot go further with this contradiction, you have to accept the fact that, accept the possibility, only only one possibility there remains. That possibility is that r can be equal to 0. So we accept that r must be equal to 0. So when r is equal to 0, 0, here you have to modify, since QF, since we have written K into H is equal to QF plus R, and there since we get that R equal to 0, this R can be substituted. When this R is substituted here, you get that K minus H is equal to QF. That means K minus H is a multiple of F. Okay, thus it has now it has become very simple, and now it makes us to conclude that K minus H is a multiple of F, means K minus H can be divided by F, that is K is congruent to H mod F. Therefore, in the first situation, that situation is that K minus H equal to F. In that situation, we got that K is congruent to H mod F. In the second situation, and that situation tells us that K minus H is greater than F. In that situation, when K minus H is greater than F, that situation also has brought us to the conclusion that it's a multiple of K minus H. If the quantity K minus H is greater than F, then that must be a multiple of F, and that is the conclusion that we have to make at this moment. That will help us to avoid that contradiction, and hence in this situation, in the second situation also, we get that K is congruent to H mod F. Okay, and that's the end of the therefore all these are explained here, and the situation is explained here. That means R equal to 0. Therefore we get that R equal to 0, and therefore K minus H is equal to QF implies that K is congruent to H mod F. Okay, that's explained. Okay, that is the end of one directional proof in one direction. Next, you can think about the proof in the conveys the opposite direction. Conveys, to prove the conveys part, to prove conveys part means you have to assume that this is true. You just think that K is congruent to H mod F. When K is congruent to H, then you have to say that A raised to K is congruent to A raised to H mod F. Right. Okay. If K is congruent to H mod F, you can write that K minus H is divisible by F. Completely divided by F. That is, K minus H can be written as a multiple of F. Okay, then since K is congruent to H mod F, that is K minus H is equal to a multiple of F, that is written as Q into F. Okay. If you can avoid that confusion with that previously taken Q, and then that Q is different from this Q here. It is written as some suitable integer Q. So K minus H equal to some suitable integer Q into F, and therefore when you use that quantity as the exponent of or as the power of A, then A raised to KH is then will be congruent to 1 mod F. That you can verify, because here you can write A raised to QF actually here, but you know that A raised to QF, since you take A raised to QF, when you take A raised to QF, that can be written A raised to F the whole raised to Q, and you have verified that this is congruent to 1 mod M. So using that statement 1, actually the statement 1 can be used everywhere. It is actually derived from the definition of the exponent of the number A with respect to the given number M. So no problem, you can use this everywhere, and then using that you can reduce that. Actually this quantity here, actually we take that A raised to QF. This is used as the power of A here, so A raised to QF, but you know that A raised to QF is congruent to, but when you use A raised to QF, you have to write equal to. So A raised to KH, one step here is missing, one term here is missing. Actually A raised to QF equal to A raised to K minus H is equal to A raised to QF, but you know that A raised to QF is congruent to 1 mod F, and sorry, and here when you come to this, this is equal to, this is mod M. It's because it's because of this fact. Here you have that A raised to F is congruent, A raised to QF is equal to A raised to F the whole raised to Q is congruent to 1 mod M. Actually, so it's a mistake here. I have written here. It is F. It is not F. Actually it is M. It's because that congruence there is when you convert that into 1, the modulus is M, mod M. So it's a mistake, and therefore a raised to kh, and hence we get that a raised to k. Now you can multiply both sides by a raised to h, a raised to h, and also you can write that a raised to h is congruent to a raised to h mod m. One more step, you can write a raised to h is congruent to a raised to h, same quantity, a raised to h mod m, and then after that multiplying those two congruences, you get that a raised to k minus h into a raised to h. A raised to k minus h into a raised to h is congruent to a raised 1 into a raised to h mod m. See, you have to change that, change this f to m. These two f's must be changed to m. Okay, that is the end of the proof, and thus we get that the result in that case. Okay. Next, to prove the b part, we get to b part. You can easily establish b by replacing h in the a part, in the result a. You can see an h is used there, and that h can be replaced by 0. See, in this expression here, if you take h is equal to 0, and you get that. You can easily establish the second result, result b. Statement b can easily be established. Okay, then how can we prove? Thus we get this expression. Then how can we prove that f is then divisible? F can divide phi m. How can you say that f can divide phi m? And that we are coming to that part. Thus by and also we know that a raised to phi m. We also know that a raised to phi m is congruent to 1 mod m. That's Euler-Fermat's theorem. Using Euler-Fermat's theorem, a raised to phi m is congruent to 1 mod m. Therefore, we have that in the above we can take, if you replace, okay, in equation a. Sorry, in the result a, not in the equation. In the result a, in a part of the result, the first part, if you take k equal to phi m, by replacing k by phi m, then we get that a raised to phi m is congruent to 1 mod m, if and only if phi m is congruent to 0 mod f. Okay, and thus easily that part also very easy. And from this the last statement obtained here, you can say that f can divide if and only if f can divide phi m. Okay, now we are now going to prove the statement, the result statement C. What does it say? That states that the number is 1, a square, etc. to a raised to p minus 1. See, actually this is a raised to f minus 1, not p minus 1. See, a raised to f minus 1. 1 a square, etc. to a raised to f minus 1 is the correct statement. A raised to f minus 1 are incongruent mod m. Suppose that they are not incongruent mod m. That means when we divide some of the powers, when we divide some of these powers by the number m, you are going to get the same remainder, right? So think about that situation. If you divide these powers of the various powers, these are continuous powers of m, of a, continuous powers of a. If we divide these powers of a by the number m, you are going to divide this number, these powers by m, the number m, and when you examine that, the remainders, when you compare the remainders, if you see that two remainders are same, and in that situation you have to say that they are not incongruent. That means they are congruent mod m. So you can just assume that a raised to phi is okay, then we assume that a raised to I is congruent to 0 mod m, and a raised to j is congruent to, or otherwise other way you can say that, you can think that two remainders are same, and that means a raised to I, you can think that, you can say that I and j are two numbers such that both are I and j are less than f, where I and j are less than f, such that a raised to I is congruent to some same remainder, say r mod m, and a raised to j is also congruent to r mod m. that means a raised to I minus j. Yeah, therefore a raised to I is congruent to a raised to j mod m. Okay, that's another way of writing that. That means a raised to I is congruent to a raised to j mod m. Okay, that is a raised to I minus j. You can transfer one quantity to the other side. You can then get that a raised to I minus j is congruent to, suppose that j is less than I. Then in that situation, suppose here j is this quantity, j is less than I, then you can then get that a raised to I minus j is congruent to 0 mod m. Then you a raised to I minus a raised to j. Okay, and then you can say that then a raised to I minus a raised to j, and it is not a raised to I minus j, it is not properly written there. Okay, then you can transfer one quantity from one side to the other side, then we get that a raised to I minus a raised to j. It's that expression is a raised to I minus a raised to j will be then congruent to 0. Okay, not there also you can apply that. Okay, previous step you can apply in this situation. It is not this way you can write that. See that the situation here, and this is the situation that you can apply there. So in that case, you can here think that k and h are the two numbers satisfying this here. These two numbers k and h are such that less than, instead of I and j we are taking k and h. Okay, the numbers, and this is the step which is suitable in this situation. So here you can think that a raised to k, when you divide a raised to k by m and a raised to h by m, you get the same remainders. If you get the same remainders, you can write that a raised to k is congruent to a raised to h mod m. And then and also, since k and h are, we are considering one of the two of the powers of a which belong to this group of powers, which a raised to k and a raised to h clearly belongs to the set of powers given here. Therefore k and h must be less than f. Okay, the value of k and h must be less than f, and that means you can then transfer a raised to h to, and also you can assume that k is greater than h. Here we assume that k is greater than h, and then you get that a raised to k minus a raised to h is equal to r into m, and that's in this situation. That is a raised to h. A raised to h into a raised to k minus h is a raised to h into a raised to k minus h minus 1 is equal to a raised to k minus h minus 1 equal to r into m. Okay, and also since you know that the GCD of a and m equal to 1, we have previously discussed this thing. The same discussion is valid here also. Since GCD of a and m equal to 1, then it cannot m cannot divide a, and m cannot divide any other power of a, any higher power of a. So m must divide. Therefore m must divide a raised to k minus h minus 1, and that is the quantity which is given inside the bracket. So m must divide that quantity. M must divide that quantity means a raised to k minus h this is the situation, this is the conclusion. So a raised to k minus h, this actually implies that a raised to k minus h is congruent to 1 mod m. But you know that k minus h, since k and h are the numbers, positive numbers less than f, both quantities are less than f, and also since k is greater than h, we have taken that k greater than h. Therefore k minus h, the quantity, you can think about the quantity k minus h, that difference, that will be clearly less than f. So you can now think about the meaning of f. As per the meaning of f, as per the definition of f, you know that f is the least number having the property that a raised to f is congruent to 1 mod m. But you have now obtained that a number, a positive number k minus h, whose value is less than f, and that also satisfies the condition a raised to k minus h is congruent to 1 mod m. But that is a contradiction. It's a contradiction. It cannot happen. Actually, that means k minus h cannot be a quantity less than f. Okay, therefore therefore you have to say that here you have to say that you have to understand that you have made a mistake here. What is that? What might be that mistake? The mistake is that that assumption that you loosely taken that when you divide two numbers, two of these powers by the number m, you are going to get the same remainder. So the steps given here is not actually correct, and these steps must be replaced by the steps and the explanation that I have given now. Okay. With this we have obtained that contradiction, and that contradiction tells us that you have to correct that assumption, that those assumptions that you have made, that you and you have to say that this number is 1a, a square, etc. a raised to p minus 1, a raised to f minus 1. It's also a mistake. In the number a raised to f minus 1, etc. are all incongruent mod m. Okay, that's the end of the proof of the C part also. Okay, with this I am going to end this video. Thank you.